This is a electric arc furnace with something more. This is the arc. This is the high current system.
Yeah.
This is the reactor. Oh, I have made a mistake here. It's in German and in English. And when I sit in English, you can read it more. So, and this is a program who takes all things. We have here parallel furnaces.
Yeah.
We have here filter capacities, and we have here TCR. And then we have here a cable, step-down transformer, and here the overline, and the power supply system. And all this program calculates the values of the high current system. And it is important to know the reactance. The reactance...
Yeah, this is our, from the furnace.
What we make in post-reactance calculation is only to calculate 3 values of the high current system. The others, sorry, Mr. Tim, the others we don't need here in this lesson, but it's an overview why we make this. And the high current system, close with accept data. I will read a prepared file, read model from, that's the same as in your program, and then all is green, and all values are input here. And the only thing we make here is the reactances of the 3 phases. We put in here, and then we can make with this program a lot, and we can take a table, and we can choose all other values here. The most important is, I think, that's the power we put in. The power, that is the current of the arc and the power. And all other values which are here can be also calculated if you choose. And this is important for the furnace that enough power comes into. And what can we do? We can have here a cycle diagram. You know already, no? But if you change the reactance, the power changes. You know. Close. And what can we see here is you can put in all 3 reactances, and if they are not symmetrical, you can calculate it also. Take table, but not also. Not all values are a solution, because the sum of the current has to be. We have here also currents between 10 and 30, and you will see here we have PA, PB, and PC. The power in percent, and you see sometimes is we have symmetrical reactance here, and if you change the symmetrical, you don't get a symmetrical power, and therefore we have to calculate the reactance, and this is only which we will do here. But I will close this program. Close.
Well, this is the main formula over there. It's not from the paper. The power of a system which is symmetrical in each phase is dependent from the from the transformer voltage, it's dependent from the reactance, and it's dependent from the control. Phi is the phase angle between voltage and current. And this is the main formula. You see, the reactance,
Ja, das ist jetzt das Postro-Programm.
yeah.
So, and this is a program we want to tell how to calculate this reactance. This
is my job.
That's a job for 2 days or 2.5 days now. First, we want to introduce us. I think that we tell what we have done before and which study we have. Are you all electrical engineers?
Yeah.
Both?
Yeah.
Mr. Eam too?
Yeah.
Electrical engineer. Have you heard something about Maxwell's theory? Maxwell's theory? Or not so much?
we learned in university.
Not too.
I don't remember.
If I would ask my students, they would say, I never heard it. And I prepared it so, I prepared the book also so that we have in the first chapters.
You have this. This is my name.
Oh, thank you. This is my name.
Okay?
Yeah.
I have your card.
Yeah, I
That's
Yeah.
This is my name.
Okay, thank you.
Okay, thank you.
So, in this book, some chapters are very important and some chapters are only information. I think you already heard about this. In chapter 1 and 2 there is many of theory, but for calculation of EIF reactance you don't need the most of them, but all red things you know, have to know if you have. But I will go step by step. We will talk about some equations and then if you have questions, otherwise we will go through the... but I think important is what is a reactance, what is a mutual reactance, what's a self-reactance.
Yeah, that's right.
It took a long time that we developed this program with Professor Tim. I think we started 1984.
Yeah.
1984 we started with developing a DOS program.
Yeah.
We only typed in length of the electrode arm, diameter of the electrode arm, and if you were wrong, you have to start it all again.
Well, we used the formula of this book and calculated this by hand.
Yeah.
And later we have written a program in some steps.
So, and this is a chapter 1, and we will start with chapter 1 on important abstract of this chapter, again in red color. I will show you some black equations, but I will say that it's important. It's necessary for theoretical, but not for calculation of EIS. So, this is a very, very short abstract of my lessons. I have a lesson at the University of Applied Science in Wilhelmshaven. I make three terms, and in each term is 6 hours a week. And we can't do this all 6 years, no. But I have some formulas here. This is a formula for the electric. I wrote the book, and I know all the things in English. Feldschreiber of English. I'm not prepared here. Magnetic field intensity. Magnetic field intensity of one winding of an iron coil. And this is a I mal N is what? It's a Durchflutung we call in Germany. I think it's ampere turns.
Yes.
Ampere turn. I think you have heard it in basics of electrical engineering. But I need this formula sometimes to explain something theoretical, not important for EIF, but we have some time, and I think we will do it. But afterwards, I think this is examples very important for you, no? So and if you have here some copper-plated arms, how calculate this and that, and we will go. But these are basic formulas, and what is not so important, but how we calculate the reactance for electrical arc furnaces. That's about the energy which a field has, and that's a very complicated. I never calculated this, but there comes out some formula, and we call it in Germany and in the Western world the von Neumann'sche Doppelintegral. And this I want to tell you what is it. Otherwise, you can't not understand how to calculate this. I will try it. So, and the induction law. The induction law is the basic of all, and the inductivity of one coil of iron. You know already out of school or out of study, and this is how you call iron coil, but it's not so important for EIFs. So that's the induction law. You know, the induction law has two directions. One induced voltage. And the voltage at two difference, and I think for EIF it's not important the direction, and important is that the dependence between the voltage and the current. I think that's a basic formula, and then it's important to know the inductance. That's the self-inductance, and you can calculate this. We don't need to do this in this. We can calculate this about the induction law. If you put in the magnetic flux phi and all the formulas, you will get this. And this is the self-inductivity of iron coil. But in EIF we don't have iron coils. We have coils. We have only conductors.
Yes.
And this. In first overview, I told you that the inductivity or the reactance is very important for the power we get in it. And therefore, we have not to calculate this inductivity about this formula, but I will show you. And how all programs work, I think you know the complex transformation. Complex AC calculation, you know. We have two things here. We have the inductivity, the inductance, and we have the reactance. And first we talk about inductance, and then in the second part of the lesson we will only talk about reactance. it's only the factor is 2p 1 times frequency, and frequency is 50 cycles per second, or in America. I think you have 50 cycles per second.
60.
60?
Yes,
yeah.
Korea
Korea
is
60.
I don't know. I don't know if I have a note. Is I thought in Japan they have two different. America has 60, and I thought all the continental has 50.
America is I think 60 years.
60 years.
Yeah, in Asia area is 50 years.
And in Korea,
Korea is different.
But for these devices, it's only a problem. But you have to put in all the factor 1.2. Okay. Angular frequency, all this formula signs, you know. Okay. So. If you calculate, you have so much reactances in the ERF. What is we just talk about self-reactance, but if you see here, we have we can say here is current 0. We have two coils. This is current 0.
Yes, current 0.
Current 0, and here we have current.
Yes.
And then we have a magnetic flux of the coil 1. And this magnetic flux passes coil 2.
Yes.
And at the last page we have had the inductance law. And if through a coil passes a magnetic flux which variated by time, we have an induced voltage. So we go to this here, and if this current is an AC current, this changes, the magnetic flux changes, and we have here an induced voltage. And this induced voltage, how can we calculate this induced voltage? That's the question. At this dia we say only there is we have some equations about the magnetic field, and then we get a and if we make it with the second coil also, we have then induced voltage here, and they are coupled. And if we make this one, we get here. The red one is very important. We get here some equations, and this is a matrix equation. We have had U is like U equals L dt.
Yes.
This is for one coil. For two coils, we get this red one. We have for two coils 1, 2, 3, 4. 1, 2, 3, 4. But they are equal also. We have 3 inductivities for two conductors. How many conductors are in the 20, 30. But we make little steps. So, so this one was a self-inductance. Self-inductance. We have two coils. Each coil has a self-inductance. And we have a mutual inductance. And this mutual inductance is the same from 1 to 2 as from 2 to 1. But of course the coupling is the same. Okay. In the next steps, we will talk not about inductance, but we will talk about reactance. And the same as here, we have said x is like x equals omega L.
Yes.
We can say here x. We have mutual reactance, and this is self-reactance. And all this mutual and self-reactance of the ERF we have to calculate. So, Mr. Tim,
Yeah.
you know this. You know this.
Yeah.
But I think this is not complete. This is not complete here. We have here only the mutual and self-reactances of was heißt Bereich?
What?
Bereich?
Area.
Area of the area, transformer line, furnace cable, electrode arms, and electrodes. We have coupling between this here, between this, and on so on. But if you show this in this picture, we wouldn't see anything.
This is the first furnace with current conducting arms.
We calculate the reactance by manual by a computer.
You see that?
Manually.
You see that part here? These were current conducting arms,
Yeah.
and this was a try to make a symmetrical reactance
Okay.
with the tubes. With the tubes, you see that? This is the first construction.
The first construction with copper-plated electrode arms.
But if you want to have the total reactance, you need there was also these were two different parts of electrodes. There were these were graphite part, and the upper part was water-cooled copper cylinders. Yeah, they tried to reduce the graphite consumption and used for the first part here copper cylinders. But this was not very good because later they invented the spray cooling with water. And therefore, this is the reason, because we have here and here different parts of electrode. And this is the reason for this construction. Yes.
Okay, we calculated this reactance with a pocket calculator, but with a pocket calculator we don't calculate this coupling because it's an enormous work. It's if you see.
You can try it with this book. A hand-written calculation of the total reactance.
If you see this here, this program you know, of course, read model data from file. I did not add all this reactance of the areas, but I think it's a little bit different between the total reactance. The total reactance, which is given here in this area here, for the three phases, we consider all reactances, also this one, and this one. There's only a loop in the program. to calculate all these reactances. And then we have to from each conductor to each conductor we have to calculate the reactant, and then we have to put it together. The reactants we have to put all together. But how to do? I will tell you. Okay, we will close this.
We mean,
Yeah.
you mean the total reactance is consider this area to effect.
Yeah.
Oh, so this part, this transformer, flexible cable, this part is only consider this area.
This is only this area.
This is
Also, if flexible cable, we have only the flexible cable. Seilfahne auf Deutsch, Herr Tim?
Seilfahne, the cable end.
Cable end. The cable ends are also in the reactance with it.
Yeah.
For the flexible cable. And I did not add here all the things, but it's nearly the same, but it's a little bit different if you have to consider all and you have the possibility to make per area 1, 2. For this area, you have the opportunity to make 8 conductors. For the flexible cable, we have 5 conductors. That's a flexible cable end, and the electrodes are only 1.
And this is a cable end.
Yeah, that's right.
You know.
Yeah.
Yeah. Okay.
Okay. But how to calculate all the reactances? I will close. I think it's a little bit changed because of the beamer. I will not save, and we will go to the presentation. And although we will not start with a complete reactance calculation, but now mathematics from the school, how I tell the students in my lessons how to calculate. We have 2 long conductors. They are very long in respect to the distance. And then we can calculate about the Laplace. I learned in English you have to say Laplace law. Laplace. Okay. And you can hear the flux, the magnetic field intensity, and the flux density of the magnetic field. And if you calculate this, you will get such inside and outside.
Yes.
And superposition, you will get this one. And if you calculate between the conductors the flux, and now we calculate the flux between the conductors, and then we get phi. This function for E, and then we say U is n d phi dt, and then we will get U is L di dt. And so we can calculate this inductance. That's a self-inductance. And you have to add to superposition the flux, and then we will get the inductivity. That's the known inductivity of long conductors parallel. But if we make afterwards the method of ERF reactance calculation, we have to calculate the same here. And this formula is what says this formula. We have two reactants. We have this comes because the magnetic flux is inside the conductor.
Yeah.
Also, we have an inner inductivity, and this is that is the outside inductivity. Every time you have inductivity, if you have not the current at the surface at the conductor, you have an inner inductivity. There's an additional one. Sometimes we don't calculate this, sometimes we calculate this. Okay, but this is a formula, this is a red. With this formula we can make examples. On this example I calculate with normal methods and then with an additional method, and this is a EIF method.
I have a question.
Yeah, to the last one.
It's possible to know the y divided 2? This.
Yeah, because this I tell my students every time, but nobody asks about this.
Yes.
So this flux is that,
Yeah.
and that goes not through the whole winding,
Yeah.
only for the. It's only through the half winding,
Yeah.
and not to the whole winding. It's only an approximation method that students learn this formula, but this formula is correct. We see out of the next theory. We have a flux. This flux goes only to the whole, to half of the conductor, not to the whole conductor. That you have to have only the half of this. Okay, and then you mach ich here. I think I have the wrong direction here. So, now we have the example on the next page.
Yes.
I think I don't have to calculate this, or shall I tell you how to calculate this?
Yeah, calculation is okay. We audition the calculators and like program.
It's only to put in a formula. But I think we shall do other things. But if you to each example, here's an example.
Yeah.
To each example, there's an exercise. And you can, with this data, length of 3 meters and so on, you will get this result. I have thought, if you would be now my students in my lesson, I would say, now calculate it. But I think in the book there is written for exercise for the reader, and you can see if you have understood this theory.
Yes.
Is that I think we need not calculate this reactance of the exercise. Herr Tim?
Was?
Ich glaube nicht, dass wir das ausrechnen sollten jetzt. Oder sollten wir da jetzt die Übungen machen? Nee, ne? Das ist so einfach.
Wir haben erst eine halbe Stunde rum. Sie müssen sich vorgeben, was Sie in den ersten 1,5 Stunden machen wollen.
Das habe ich nicht.
Nee?
Das mache ich in Vorlesungen auch nicht. I do not do a plan for a lesson. I make the lesson, and if next time I'm too slow, I will make a strong time.
Aber bestimmen Sie das mal, wie Sie...
I think we don't. I thought you would calculate, but for the understanding, we have another exercises for you. Okay, this is what I tell our students. They don't know something about self and mutual reactant, and then I have a series coupling of inductance, and if they have inductance, you see it's not if you have without coupling, you have to add the inductance of the 2 points, and if you have a coupling, you have to calculate the coupling. And this is the most important thing also for ARFs, that you have to all the couplings between all the conductors. And that's here in red. The reactance with coupling is different to without coupling. And for the post-group reactance calculation, it means the total reactance is not the sum of the reactance of all parts, but almost. I already told you.
Yeah, I think 2 graphic is same, but why without magnetic coupling and second with magnetic coupling? Only calculation of this formula, that's right. So I think my question is same graphic.
Yes.
But in purpose different.
And you don't have to calculate this. If you say the coupling M is 0, you have the same formula. But important is that you have a coupling between all things.
Yeah. In this case, without magnetic coupling, this case is we can see the in express we can see this style of cable.
There's also a coupling if you have two conductors in series.
Yeah.
You have to calculate the self-inductance, and the mutual inductance, and then you have to combine all the 4s. Yeah. But we will see a little bit in future. Okay, for parallel, for parallel, it's the same. But the theory is a little bit complicated. You have to inverse the matrix and so on. But it's not important. I don't need VLAN, the internet. But I have internet for the that are the important equations for calculation of electromagnetic fields. Or the Maxwell equation. An application engineer of ARFs don't need this, but he needs the results. But we have 4 Maxwell equations. The first Maxwell equation was also integral, line integral harmony is the V, is the current V response. That's the integral one, and this is the integral it's the same equation, but in other form, with differential. This equation is the same as the first Maxwell equation. This is the first. The second Maxwell equation is U is in the induction law. The induction law in this form is the second Maxwell equation. The third Maxwell equation is only from electrostatic fields. We don't need, for ERF calculation, we don't need the electrostatic field. And the fourth Maxwell equation is, if you call the magnetic flux P is like integral B dA. That's the same. If you calculate it over a whole area or whole volume, then you don't have magnetic charges. Therefore, you have the Maxwell equation integral B dA, B dA is 0. So here's the current density. The current density is the conducting. That's Ohm's law. Ohm's law is E is like, that's Ohm's law.
Yeah.
And if you put it in field theory, you will get this current density, and you have a Verschiebungsflussdichte in German. Verschiebungsflussdichte in German. Displacement current density. But it's not necessary for calculation 50 hertz or 60 hertz. You don't have this displacement current density. And then you have the material properties. But all these formula are not right. We don't need for ERF calculations, but only for background. And the next time I put here all the Maxwell equations in blue, which we saw at the last page. And we can convert it this to differential form. This is the integral form, and this is the differential form. That's the same. That's the same. You will get over this over the rule von Stokes. You will get it, but until my students, nobody knows it. All this is very complicated. Afterwards, we have some results out of all these equations. You are already asked of one question in the email. You asked about this. We will see it and will answer about it. And I think this formula has to be in green because this is a differential form. This is a differential form, and I have to put it in green. Okay. So, and that we have electric charges in a volume that is a volume, the charge density, and no magnetic charges, so divergency is 0. And we have 4 equations. We have 4 equations. These 4 equations that are differential equations for 4 variables. Sorry, I have a cold. And yesterday I was so ill that I thought I can't make the seminar here. But you are here, and so. And how to and this is a calculation of vector. We have 4 vector variables. How to solve this? We have to put in all the things. We have to have one differential equation for one variable. And we want to calculate if you have current displacement, you have to calculate the current density in a conductor. And how to do this, I want to tell you here. It has afterwards some influence to the reactance of a tube. If you have a tube by this, you have an outside radius. And you have an inside radius. R1. But if this is for copper at 50 Hertz, more than 1 centimeter, we have only a current displacement to the in outside. That we have this one. We have, for example, 60 millimeters. And if you have here 40 millimeters, it makes no sense for the electrical. You have skin depths. The skin depths I call sometimes somebody call it H, or somebody told it D. You have only this. You can forget for electrical, but the construction engineer says, "I need this because this, it has to be mechanical stable." No? But for an electrical engineer, the H is 9.1 millimeters at 50 Hertz. And if you, I think it's in Korea, it's a little bit smaller, about 9 millimeters at 60 Hertz. We can calculate, but you know, I think. But how to calculate this? You need all this differential equation, but nobody of an electrical engineer's capable. Nobody is not correct, but 90%, 50, and 95% of the electrical engineers do not calculate all this differential equations. They say also if you have an electrode arm, 400 millimeters, 600 millimeters. If you have only 1 centimeter, the current is only goes only, and then it's easier to calculate. This 1 centimeter does not matter in the reactance afterwards. But in this book I showed you how to calculate this, and it's not necessary, but we have some time, and then I will show you. We have four equations and 4 variables. So we have to put in all together in one equation. And this, I don't know if you have in Korea rotation or if you have the Laplace sign. In Germany, the physicians use the Laplace signs, and we have divergence, gradient, and rotation. Do you know this vector operation? I think it's not necessary to know. but you have to put in all these differential equations in one, and then you will get this one for the current density. This is then you have only one equation, differential equation, for a vector with 3 components. That is this one. You have here the delta is the second derivation of the current density in x, y, and z. And so the whole set of the differential equations are this one. And I never solved such equations, but only in one dimension. So this is what, and then we have to do the same as here. We can't calculate the time dependence. The time dependence we put in J omega. And then we have a complex differential equation. The time dependence, the time dependence here goes to J omega. From U is like L di dt, you say U complex is J omega L times d. And so we'll do the same with the current density. And then we will look at this one. We have a conductor. The current density goes in that direction. We have no current density in x or y. So we can strike out this components of the differential equation. Then we have no dependence in z. That's the derivation to z is 0. And then we can calculate something. We say we have here in y, we have only a small compared to the spin depth. We have a very big conductor in y, and so we have no derivation in y. So we get a normal differential equation we can solve with methods or mathematics from this study, or without field, many field experiments. We have also one complex differential equation of the complex current density in z direction. So, how to solve this? We solve this. We make a proposal and we solve this and we get a solution. This solution is important. That's a differential equation of second order. To have two solutions, but only one solution is available. Because if you have high current, we have a small spin depth, you have high current suppression. Yes. And then you have only here current and not here. Okay. And if x goes very big, it has to be very small. So we have here in x only the minus sign. This gives the big value that we have only one constant, and we have that's the current density with the a function is less. So if we have here, when I put here that's a conductor,
Yeah.
and the current density. That's if here is x, we have here your that's null at the outside of the and this the current density decreases from the outside to the inside, and if you have high current suppression, it becomes zero. That's important. I already told you for the reactance calculation you have also to use the outside of the conductor. But you don't need to calculate this differential equation, but you have to know this formula is in red, all this formula, and then it's important for you. And this is important. You have to don't calculate the current density, but you have to know the current density decreases from outside to inside. So, the next one, to calculate the resistance and the inductivity, the inner inductivity. The conductor has an inner reactance and an outside reactance, and so on this sheet is calculated we have time if you want. Okay. How to get this value of the impedance Z? The impedance Z, you calculate the current, and the current is the current density, the integral of the current density about x. And then you say at the outside of the conductor we have J0 is kappa times the electric field strength, and you can say kappa, and so you have a formula between E and U. Here, E and U. That's the solution of the differential equation. But the result is important here. You will get this formula for Z. What means this? Z is voltage divided by current, complex, and so get this. What means it? It's a factor here. What is this? That is R. What is this? I think I will show it at this paper. And I will tell you the results. So, if you have here the outside radius R, you have here the spin depth H. H is so, and if you calculate, R is like how I learned at school. L is the length of the conductor. Kappa is the, and what is the area. And the area, if you have here, this area is 2p r bar times h. So, that you have to put here that you get the electrical resistance in this formula, and this is here written here. That says, if we have to calculate the resistance of a conductor with high current suppression, we have only to take from the surface the skin depth. That's important. That's very important. That's important for the reactants afterwards too, because for the reactants you have a conductor, and this conductor is not if this is the inner radius, the inner radius is not important for electrical. That is a very important of this theory chapter. I don't know why it is not read. It must be. I think it has to be read here. The second one is, if you have high current suppression, then the impedance of the conductor is in R and X the same. You see here, the real part and the imaginary part is the same. For the ja.
Das hat geklappt irgendwie.
Das ist die Eingangstür.
Ja, wahrscheinlich kommt. Ja, Sie dürfen ruhig reinkommen. Tante links.
Alles links?
Ja, hier auch.
Das ist nicht so.
Jetzt hat er die. Los. Finde ich gut. Das geht alles auf mein.
Geht alles weiter? Ja. Okay, alles klar.
Müssen, wenn Sie eine Unterschrift brauchen, schon mitnehmen.
Wenn wir Ende der Woche müssen.
Ja, okay.
Gut. Vielen Dank.
Okay. And there's a second example. You have a copper bar, bus bar. Copper bus bar. You have BS 20. That's 80 kilohertz. That's 80 kilohertz. It's not 60 hertz. There you have there you have an skin depth. I don't know how, but it's very small, I think. And here is also a solution of the differential equation. And I don't want to tell you how to do this. It is explained in this in the book.
Yeah.
But we want only to discuss the result here. And here is also the same. If you have high current displacement, you have the same as the last example. And I will tell you, for high, you have to decide, do I have high current displacement or small displacement? And if you have high current displacement, I will tell you how to calculate the resistance of this bus bar here. High current suppression, you have here the length 20 millimeters. 20 millimeters. And here you have 2 millimeters. So, how to calculate the resistance? You have to calculate R is area A. What is the area A? What is the area A? And you have to put here. No, you have to put here. This one is the area A. You have here the current spin depth H, and here. So we have to calculate A is 2 times, and this was B. And A is not from the point. So you can put in here and calculate this for bus bar. It's an example for bus bar. In AIFs you don't have bus bars, but you have copper-plated electrode arms, and if you make copper depths of 2 millimeters, of 20 millimeters, it's too much. It makes no sense. A is via L. Okay. I want to tell you that the current displacement is a very important influence to the reactants and to consider. But sometimes the mechanical engineers say, it's not enough, I have to make it C. But they have to calculate the short current, what heißt Kurzschluss?
Short circuit.
Circuit, and if you calculate the forces, the mechanical forces to a bus bar and also to an electrical furnace, the mechanical engineer has to consider this. So, and here I made if you have this this example here, it's the same from the last page. If you see, if you calculate this, here is varying this one, and we have here the skin depth of 0.5 millimeters. That's not shown here, but in the book you can see it, that we have a skin depth of 0.5 millimeter, and if you want to calculate the conductance, this conductance is in the inverse resistance. You will see that if you take the exact formula, you will get this one. And if you calculate with the skin depth in this matter I show you, you will get the blue one, the approximation. And there's only very less difference between this. That means we can calculate all the resistance if we take part the skin depth from the outside. And then we have, I think,
Is C in S?
in,
Oh.
I will explain. The first that we are asking. That's the resistance,
Yeah.
and that's the conductance.
Conductance.
That's O.
Yeah.
Yeah, that's O. And G, it's Siemens
Yeah.
in Europe, and in America it's Mo. But this is in Europe we look at the System International, and there we have the conductance in Siemens. But if you show here the inverse, the resistance, it has a hyperbolic, and this is easier to show. But important is that the current density is only from outside the